So as Roberto said, my name's Nicole or Nikki Scott, and I work for a company called Smart Material Solutions. We are in Raleigh. We spun out of NC State about, I guess, 6 or 7 years ago, but we are on campus at NC State using their focused ion beam setups, I don't know, several times a week. So I'm going to talk a little bit about what we do on the focused ion beam, some tricks and tips we've learned along the way, and then end with a demo of us actually using the Quanta FIB at NC State. That's a gallium FIB. But before I get started, Roberto actually asked me to talk very briefly about what we do at my company and how we use FIB to make everything happen. So I'm going to give just a brief introduction to what we actually do before I jump into the details of the FIB. So at Smart Material Solutions, we focus on a process called roll-to-roll nanopatterning, where basically you start with a smooth film and you use a mold that is cylindrical and has some type of nanopattern on it. You press that mold into your film, and either through heat and pressure or by a UV curing process, you transfer your pattern onto a film. And by doing this, you can create very large areas of patterned films. And on the right here, I'll show a video of one of our molds patterning a film with, in this case, 300 nanometer features. So this is a picture of a short piece of over 500 feet of the film pattern in the video on the last page. And here is an SEM of that film. So this is a pretty cool way, I think, to create very large nano patterns, because we can very quickly replicate the nano pattern on just this small mold over hundreds and hundreds of feet. And there's tons of interesting applications. I'm sure some of you probably work on some of these applications in your own research. And we're just focusing on taking the cool applications that use nano patterning and scaling them up so that they're actually manufacturable. So what we do is we actually focus on making this mold, this cylindrical mold. It's a pretty difficult process. You probably have done some type of nano patternings, whether that be electron beam lithography, interference lithography, etc. But as you know, those processes can be pretty slow. So what we do is we take a diamond and we have a nano pattern in it. So this is an example of our nano pattern diamond. We indent it into the outside of a rotating cylinder. So this is like a very fancy lathe. And then we have very precise control over the rotation of the cylinder and the movement of this diamond die, such that we can coin these features into the outside of a drum and stitch together the features in a seamless manner. So this is kind of our thing. Now, the thing I don't show you here is that this is extremely slowed down. So our process creates about 50,000 indents every second, so we can cover large areas pretty quickly. And on the right here, I show an example of our process. And you can see, you can't actually even see that this diamond die is moving, but it is. And you can see this diffraction pattern growing while we talk. This is all done in real time. So this is our patterning rate using this process. So we can very quickly cover large drums that can be used in roll-to-roll processing. So why do I tell you all this? I haven't even mentioned FIB yet so far. Where FIB comes in is we use FIB to make these diamond dies. So we can create a variety of precise patterns that we can then use for indenting into our drums. So here are some examples of patterns we've made for my company. We've made nano features with pitches down to about 200 nanometers. Micro features and micro lens arrays. We can have, for our process, gone up to about a 10 micron center to center distance. But of course, with FIB, you can go even larger. We've made some pyramids, hierarchical features, which are nano features on top of micro features, linear gratings, stochastic features, so more just random features that are sometimes nice because they get rid of diffractive effects, and arbitrary features. So this is our company logo that we made a couple years ago. And another arbitrary feature that we made, I want to talk about very briefly. It wasn't really for work, it was more for fun, but this is my engagement ring. I got married last year, and then I took my engagement ring, I threw it in the FIB here at NC State, and I patterned one of the diamonds in it. And as it zooms in, you'll eventually see that it's got our names on the side of one of the diamond facets. So you can do some pretty cool things, I think, especially when you look at arbitrary features that you can pattern into different things. So this was done with the FIB. I've got my ring on right now. And if you look very closely in an optical microscope, you can see our names. All right, so now I'm going to jump into the details of FIB nanopatterning and how we actually do what we do. I do want to talk about both nano deposition and nano machining. So everything that I do for work is nano machining, where we're removing material. But there's also a very powerful process of nano deposition, where instead of removing material, you're actually adding material. It's kind of like a nanoscale 3D printer. So I'm actually going to start by talking about nano deposition and then transition into nano machining. So for nano deposition, one of the processes is called ion beam induced deposition, or IBID. And to do this process, we use usually a needle to insert precursor molecules. And exactly what those precursor molecules are going to depend on what material you're trying to deposit. But regardless of what they are, you can either use an electron beam or an ion beam to cause those precursor molecules to react with each other and form a deposited material. And therefore, by scanning your electron beam or your ion beam across the material, you can control where material is deposited. And I have some pictures here, some really cool things. I didn't do any of this. I stole this from literature, but there's some really cool stuff out there. So this is an example of a standing stick figure that was made using IBID, where they started with the legs and then, just scanned the beam to make a 3D figure like you see here. So obviously you can do some pretty cool stuff. As I said, it's kind of like nano 3D printing. And then here's a couple of other things I've seen in literature that I think are pretty cool. We've got a virus, we've got the Leaning Tower of Pisa, and for all you Star Trek fans, we have the Enterprise. So yeah, I think that you can do some cool stuff. As I said, we have not done any of this, but there's a lot of interesting information out there if you're interested in doing this. And I know this is a capability you could technically do at the NC State Quanta FIB, because there is, for example, platinum deposition. So you could make something like this with platinum if you had very good control. All right, so now I'm gonna switch into FIB milling or FIB machining. This is where I'm gonna spend most of my time, because this is one where I have the most experience and I feel like I can, provide the most interesting information. But two, where I'm going to do the demo. So basically, when you're doing FIB milling, you have an ion beam. So in this case, these are the little pink circles here, and those represent gallium ions. And you shoot the ion beam at your sample, which in this case are these little gold atoms. So when you shoot your ion beam at your material, a couple of things can happen. first of all, some of the gallium ions can become implanted inside of your material. So you're always going to have some implantation of your ion into your material. You can also knock off atoms from your material. So this, in this case, is these gold atoms being sputtered away. And that's, the primary mechanism by which we're, machining this material, because we're removing those atoms. One thing you have to pay attention to is that some of those atoms can shoot off and then redeposit elsewhere. So that's what this is here and here. Is atoms that have been sputtered away but haven't fully escaped the material because they end up redepositing in an adjacent area. And I'll talk a little bit about redeposition and methods we can use to control it, but it's definitely something you have to consider when you're doing FIB machining. And then finally, as you guys know, you can have secondary electron emission, but I'm probably not going to talk too much about that here. So this is the same slide I showed before. Using focused ion beam milling, we can create a variety of features, and this is just a selection of some of the things that we've actually made at my company. So one thing you have to consider when doing focused ion beam milling is the beam shape. So the beam, you might have a beam center at a particular point where this X is, for example, but you have to realize that if you have your focused ion beam centered at the X, that you're not only milling at that X, at that point, because the beam has a distribution. You're going to have most of your ions at this point it's focused at, but you're still going to have some ions as you move away from that point you're focusing at, to the point that even many microns away, you might have, depending on your current, you might have a tiny bit of fibbing. So you might fib a little bit when you're moved, just a small amount away from your center point, and even less as you move farther away. But that means you're not just removing material from a single point. And as a result, this isn't, when you cut just a line, instead of getting, a nice point with sharp, like straight vertical edges, you end up with something that resembles your beam shape. So this is an example of a line that was cut in a material. And you see that you don't have vertical sidewalls. You do have this, this trench that resembles your beam shape. So I think that's one of the most important things to remember when you're doing some focused ion beams and focused ion beam milling. And I will show you an example when I get to the demo of how we can actually take advantage of this, but how it can get you in trouble as well. Another thing we have to consider is that the sputtering rate depends on the angle of incidence of the ion beam with respect to your sample. So here is a graph showing the sputter yield, so the number of atoms you sputter away per ion that you're using, versus the incidence angle. So at 0 degrees incidence, that means your beam is normal to the surface you're trying to sputter. And you actually have relatively low sputter yield. And the reason for that is that an ion beam, the ion comes in vertical in this case. And then the atoms that are escaping have to almost, go 180 degrees difference to shoot back out in that same direction. So, the momentum has to change direction. So it's not a very efficient process. However, if we go to say 80 degrees, you see that the ion beam comes down and the sputtered atoms don't have to shift direction quite dramatically. So we can have much more efficient sputtering in that case. And this has pretty big implications for when you're trying to pattern features, because let's say you have this feature here and you're trying to refine the feature shape. If you just had a ion dose that was constant for all positions in this, around this feature, you would not actually sputter every point on this feature the same amount, because here you have an instance angle close to 0. And so you're having a very low sputter yield. So you're not going to efficiently sputter material here at the top of your feature. But at the edge of the feature, you're close to 90 degrees incidence angle. So you're gonna have very quick or very efficient sputtering from that point, which means that if you sputtered this entire feature for the same amount of time, what you would probably see is that the feature would not get very much shorter, but it would get a lot skinnier, because you'd just be eroding away those sides much more quickly. So when you're thinking about sputtering or FIB milling something, you really do have to consider that you can't simply, sputter more at the place you want, more material removed and assume that it's going to be a linear relationship for another, there's not a linear relationship between, the amount of time you sputter and the amount of material you sputter because of this angle incidence dependence. The other thing, as I mentioned, that you have to consider is redeposition. So on the left here, I show an image of creating a trench. So if you start and you're scanning back and forth, you will get some redeposition as you at the edges here, because material that's removed from this bottom is likely to hit the side. Well, some of it is likely to hit the side and then reattach. And then as you make your trench deeper and deeper, redeposition is becoming more and more of a problem, because when you're sputtering material from the bottom of this deep trench, the chances that it's able to escape this trench without hitting a wall and redepositing becomes smaller and smaller. So definitely something you have to consider. On the right here, this shows that if the direction of your milling is important. For example, if you start milling on the left side and then you move to the right here, you're going to continuously be redepositing on the left side. Now you're also redepositing on the right side here, except you're moving to the right, so then you're removing that redeposited material as you go along. So this is something you should consider when you're milling, that your scan direction does matter. And I think I have a couple of examples of how scan direction and the number of passes matter. So when I say number of passes, oftentimes when you set up a milling process in the FIB, you can do a single pass, meaning the FIB is going to, the beam is going to move along the desired path one time. You can also do mini passes, where it removes along that path once and then repeats and then repeats. And you can compensate with the amount of time your beam dwells on each point, such that the total amount of time you spend at each point is the same. So in this case, on the left here is a single pass. The ion beam only touched each point one time, but it dwelled for a total of 882 microseconds at each point. And on the right, we have 882 passes, where the beam dwelled at each point for only 1 microsecond. So you can tell that the total amount of time spent on each of these patterns is exactly the same, but we have very different results. And the reason is, since we only go over this one time, everything that's redeposited is redeposited at the time that you're making this one pass, and you never come back and clean it up. Whereas if you're on this one on the right, you've made the one pass, and during that one pass, you've made a bit of redeposited material. But on the second pass, you kind of clean up that redeposited material, and you continue to do that for each 882 passes. So one thing that you can do to help control redeposition is, if you have the freedom, you can increase the number of passes. I generally like to do about 100, but obviously, 882 is fine. I just don't tend to do, you can set it up to do 20,000 passes, and I've never found that necessary. So I like to do on the order of 100 passes to make sure that I can clean up my features and prevent unwanted redeposition. Another way you can avoid redeposition is by controlling the way that you scan. I mentioned earlier that the scan direction matters a lot. So I want to compare, in this case, the creation of these dots here, these circular fibbed holes, I guess, but by two different methods. I'm going to compare on the left a raster scan, where we always scan from the right to the left. So there's a directionality to all of these. And on the right, a spiral scan, where we do a spiral inside the material from the inside to the outside. And then we move to the next dot, and we do a spiral from the inside to the outside, and then move to the next dot. So as you can imagine, the redeposition is going to be very different in these two cases. Because on the left side, we're going to have redeposition preferentially on one side, whereas on the right side with the spiral scan, we're going to see that when you start in the middle of a single dot, you are going to have redeposition on the outside of that dot, but we're scanning farther and farther out for each dot as we go. And so we're therefore destroying whatever was redeposited during the earlier stages of FIB milling. So here is the result from those two processes. And in these inserts here, you see the cross section of the features. So on the left, you do see that there is preferential, the features are kind of tilted, and that's because this bit here has been redeposited. And since we're always scanning from the right side to the left side, we have preferential redeposition on the right side of our features. Now, on the other hand, when we do the spiral scan, where we always start in the center of each feature and spiral outwards, we don't see that directionality. So this is just another example where you have to think about how your features, like what type of features you want and what type of scanning makes the most sense for the features that you want to get them as symmetric as you may like them to be. So now I want to switch gears just a little bit and talk about the different types of focused ion beams. So the focused ion beam I'm sitting at NC State right now is a gallium FIB ion beam. It uses a liquid gallium source to create its ion beam. There is another type of FIB. There's one at NC State. It's the Hydra, for anyone who's familiar with it, and it's a plasma FIB. And instead of using a liquid gallium source, it uses a plasma as the source for its ion beam. And there's many types of plasma FIBs. The one at NC State has, what does it have? It has xenon, argon, oxygen, and nitrogen. Thank you. I was forgetting the fourth one. But in all those cases, you create a plasma of that gas, and then you use that to create your ion beam. So I will say, I don't think one type of FIB is better than the other, but they have different strengths. So I want to bring your attention to this plot over here. We have FIB image resolution. So kind of like how small of a feature can you make versus your current. So for the gallium FIB, which is in orange, you'll see that we can get much smaller features because we can get lower resolution. Well, yeah, you can get much smaller features because you're on the lower scale here for the resolution. But when you try to go higher and higher with your current, you eventually shoot up and you end up losing, good resolution. So at some point you can't turn up your current anymore and get a good feature. Now the plasma FIB is interesting because you see that it can't get as good resolution as the gallium beam. If you want tiny features, you want to be using a gallium beam. But you can keep turning up your current higher and higher and higher and higher, and your resolution stays pretty reasonable. And you might ask, why do I want to change my current? Well, generally, the amount of material you can sputter away is going to scale with your current because, as we talked about before, you're looking at the number of atoms that you're removing from a material per ion that comes in. And current is a measure of how many ions are coming in per second. So if we increase our current, we can increase our sputter yield. So we can increase the amount of material we're using. So the nice thing about the plasma FIB is we can really crank up the current and still have decent resolution. So I would say the gallium FIB is going to be your better choice if you want small features, but if you want big features, the plasma FIB might be your better choice. And so here I show a plot with a chart with some examples comparing a xenon plasma FIB to a gallium FIB. So you see that the sputtering rate at a given voltage is much higher for the xenon. And you can remove more volume of material per current, basically. And you can have a much higher current in your material. So the end result is that if you don't care about, great resolution, plasma FIB might be helpful for you to just remove a lot of material fast. So I want to show a couple examples where I compare a gallium FIB to a plasma FIB. As I said, if you want small features, you really need to be using a gallium FIB. So for example, on the gallium FIB, I have no problem making features where the center to center distance is 300 nanometers. It's relatively quick and easy, and you can get some nice features. On the other hand, this is an oxygen plasma FIB, and this was my attempt at 1.2 micron features. And you can see that I just do not have the resolution to get nice features. So for sure, if you want small nano features, especially sub-micron features, you need to be looking at the gallium FIB. Now, on the other hand, I want to talk about micro features. So these are some micro features I made with the same like beam paths, I would say, on different types of FIBs. You'll see that the gallium FIB in this case does have, I would say for this top row where I'm looking at 10 micron kind of micro lenses, I would say that I still think that the gallium FIB has nicer lens shapes. And that's partially because you still have, better resolution, so you can get these like very nicely shaped lenses. But you can see with some of these other plasma FIBs, I can still get decent lens shapes, and I'm doing it much quicker. So in this case, it took 106 seconds per feature, whereas these, it took only 74 seconds per feature. And this one was a little bit longer, but actually if you look, I used a lower current for some reason. So this is maybe not directly comparable. Now, when I'm looking at taller features, I can see with the gallium FIB, I was able to make a taller feature with kind of like these riblet things. And it took 280 seconds for a feature. But when I used an oxygen plasma FIB, it only took 93 seconds for a very similar feature. And I did see some funny stuff here. For example, with the xenon, I wouldn't, put too much credence in like the exact differences here. I did not try to refine this shape. I don't know why exactly this one looks like this, but I will say, I think the conclusion of this slide should be that you can create similar features much quicker with a plasma FIB, and not really say, oh, well, clearly the oxygen FIB is better than the xenon FIB or something like that, because a lot of that's going to depend on your material and exactly what type of feature shape you want. But as I said, conclusion of this slide, you can definitely do things faster with the plasma FIB. And as I said, these are the amount of time it took per feature. Sometimes you're making 100 features. So the difference here can add up dramatically. So the difference between, 280 seconds per feature for this and 93 seconds per feature for this, when you're making 100 features, makes a huge difference. All right. One of the last things I want to talk about is this other process, which I think is really cool, to pattern with a FIB, but it's not your traditional FIB machining or sputtering with a FIB. And that's using a process called, basically a process in which you use ion implantation to create an etch mask. This is a process that is known to work in silicon and in diamond. It may also work in other materials, but I can guarantee it works in both of those. And basically what you do is you use a gallium beam. Now this has to be a gallium beam. Not all FIB beams work for this, but gallium beam does. And you expose different parts on your surface. Now, when you expose these, you're not actually fibbing long enough to necessarily sputter away any substantial amount of your material, but you are sputtering long enough to implant some gallium inside of it. So sometimes when you're done with this exposure step, you end up with something that you can barely see in the SEM. But you've, in doing it, implanted a little bit of gallium, and it turns out when you implant gallium into either diamond or silicon, it creates a layer that is resistant to etching. So then you perform an etching step, usually a reactive ion etch, and you can etch away the unexposed parts of the material, and you end up with an etched material where you never had to use photoresist or any type of development or really any true mask layer other than this implanted gallium layer. And this is an example of some of the cool things that one of our partners has done with this type of process. They have a company called Adama, and they made their logo here where they basically exposed these parts with the ion beam, and then they etched, and they ended up with their logo raised in the silicon. And we've done this in our lab as well, and have used it to make a variety of nano patterns, and it does work pretty well. So it's a pretty cool process. So now I want to kind of transition into how we do patterning with the FIB, and I'll end with a demo. So what I'm about to talk about, I think, is transferable to FIBs that aren't either Thermo Fisher, which used to be FEI microscopes, but there might be some subtle changes because everything I'm going to be talking about is specific to the FEI interface. So I just want to put that out there. This is a screenshot of an example interface of a focused ion beam SEM created by Thermo Fisher. So on this top left here is our scanning electron microscope image. In this case, I've got a piece of diamond in my view. On the right here, this is our focused ion beam image. So I guess one thing I didn't really discuss in detail is that you get an image from your focused ion beam, which is pretty cool. But you always have to be careful when you're looking at that image, because when you're looking at their image, you're actively milling away at material, unlike when you're using the electron beam. But it does give you the ability to control your patterns pretty precisely, and then you can look over here in the electron beam to see how you're doing. And then of course in the bottom here, I just have an image of the inside of the chamber, so I can see where my sample is relative to everything else. So there's many tabs over here, and this currently has this patterning tab selected. And I'm going to zoom in here on the patterning tab, and you'll see that there's a lot of information. Here we go. There's many types of patterning that you can do. So you can do just a rectangle, and it's just going to fib a rectangle. Many of you may have already used either a cleaning cross-section or a regular cross-section to either cross-section a material and look at what's inside, or to do like a TEM lift-out process. So you may be familiar with this. There's obviously different types of shapes, so like circle, line, polygon, etc. But what I generally use for patterning is either a bitmap or a stream file. And I'm going to talk about both of those options. So if I'm using a bitmap, I'm literally uploading a grayscale bitmap, like the one you see on the left. And what the microscope does is it will scan its beam across this image, and any place that is pure black, it will skip. It will have, essentially, it will not dwell any time at that point. So, you know, the center of this circle is black, so the beam's just going to skip right over it. But anything that's pure white, the beam is going to stay at the maximum amount of time that you set, which is your dwell time. So if I have a dwell time of 1 microsecond, when this beam scans across this bitmap, it's going to stay at any place that is white for 1 microsecond. And then gray is anything in between. So it's maybe difficult for you guys to see here, but there actually is a little bit of gray between these features. And as a result, the beam will stay somewhere between 0 and 1 microsecond, and it's scaled by how light or dark that feature or that pixel is. So that's one way we can control the features, or control where the beam goes and how long it mills at each point. And this is an example of a nano pattern I made with this bitmap. Now, one thing I kind of want to point out, and it will be even more obvious once I start doing the demo, is that these have like decent features, and we don't have anything going on between the features, even though this is mostly black between these features. And that is because I've taken advantage of the fact that I know that there is a beam shape to my ion beam. So even though I'm not necessarily dwelling any time at this position, because I am dwelling at a nearby position, I'm essentially milling that corner piece anyways. So it's important to, as I said, keep in mind that you are milling at places you're not necessarily telling the beam to mill at, just because your beam shape has, you know, it's not just a point. Stream files are pretty powerful. Basically, they're these very long text files, and I'll talk about what the text is in a second. But the essential part is that it tells the beam positions and how long to wait at each position. I've written here, note that stream files are not compatible with drift control, which is an FEI bug that I have talked with FEI or Thermoofficial now several times about, and they have confirmed that it is a bug. They say that the newer microscopes should not have this problem. So when we get the newer microscope that's slated to come in March or April of this year, then we'll see. But right now, you need to understand that you can't use drift control with the stream file, which is a sad thing. So let me show you what these mean. So the first line is just the type of stream file we're using. S16 just means it's a 16-bit stream file. You don't really need to worry about that. But if you wanted to use a 12-bit file, you just write S. The next is the number of passes. So we talked about passes before, and I said that I like to have a large number of passes, and I do. This one only has one pass. The next thing is the number of points. So this is the number of XY coordinates that this stream file is going to go to. And then you've got all of your points. So in this case, this would continue to go on for, 49,400 and some more lines before it ended. All right, so let's dig into this. All this does is it first tells you the dwell time. So how long in 0.1 microseconds does the beam stay at this point? And then it's the X position and the Y position. And this is, some notes for you if you were to actually make it, but like what that means. But it's basically the pixel location at which you hold the beam. And unfortunately, it is pixel location, which means that if you change your magnification in your FIB, this does not compensate. If you zoom out a lot and suddenly, this pixel is, the distance between pixels maybe when you were zoomed in might be like 1 nanometer, and then you zoom out and suddenly the distance between pixels is 100 nanometers. Well, too bad, it doesn't compensate. So this is maybe an annoying part about stream files, but obviously they're extremely powerful because you can control exactly where your beam is going and how long it's staying at each point. I will say, obviously these are really complicated. Obviously you don't want to be writing 49,000 points by hand, but there are MATLAB and Python programs out there that are freely available to help you write these. So just putting that out there. All right, so I think now we'll transition into using these actually on the FIB, and I'll demonstrate patterning with a bitmap and patterning with a stream file, and kind of talk about some of the things that you can do to compensate when you see features that are maybe not exactly what you want. All right, so on the right here, or I guess you can see this screen. On the left here, I have an SEM image, and I've already pre-focused things and stuff so as to not waste your time. And I've also aligned the sample such that the electron beam and the ion beam are, hitting the same point. So in this case, you can see in this bottom right image, the sample, it's tilted, and the electron beam's coming straight down and the ion beam is coming perpendicular to my sample. So when I'm looking at the ion beam, which is the top right here, I'm looking straight down. When I'm looking at the electron beam, which is the top left, I'm looking at an angle. So I'm going to start by making some features. As I said, I've already pre-focused this, and I'm gonna go ahead and, ooh, we're really drifty. Give it a second to work itself out. All right, there we go. So now I'm imaging on the right here with my focused ion beam. I'll make it obvious that I'm imaging because now I'm going out of focus and then back in focus. You do want to make sure this is focused just like the electron beam so that you can get good, good resolution. If you're out of focus and you're trying to pattern, you're not going to get a pretty pattern. All right, so I'm going to select Bitmap and then just draw a bitmap here. So obviously there's nothing in this yet. I can select my file. Maybe I'll do the fun one first. So here is a minion. This is maybe just for fun, but maybe we'll start with it and it'll be fun. So as I said, you can use any bitmap, including, bitmaps of minions. And if I scan this, I should transfer this pattern, which in this case is just a picture of a minion, onto my sample. So I'm going to make this only take a minute because I don't want it to take too long. Well, we'll do 26 seconds even and see how that goes. All right, so I'm going to start this. I'll show you guys real pictures in a second. Pause. So you can see my minions starting to form here. As I said before, you can image while you mill, so that's kind of cool. All right, I guess I'll let it keep going. I might have overdone it so that you can't see the picture. Let's see what it looks like. Oh yeah, I overdid it. You can kind of see it if all right, let me do this again for less time so that you can actually see our minion. Okay. All right. Even then I've overdone it a little bit, but as you can see, there is a minion here. And if I worked on it a little better, you'd be able to see the minion a little more clear. I think you get the point. Like, you can literally use any bitmap to make your features. So now I'm going to go over and actually do some real nano features that you might actually want to do. So I'm going to come over here. And what I'm going to do is I'm going to get, this is the same bitmap I showed you guys before. Maybe I'll zoom in a little so you can see it a little clearer. All right. Yeah. Thank you. All right, so you should be able to see this bitmap. This is the same bitmap I showed in my slideshow. You see that it's literally, black in the center of these features, but as a result of it being truly black, it's actually rendering it as nothing because there's no fibbing that's going to happen at those points. And then everywhere that you see something that is visible, it's either white or gray. So there's going to be some amount of fibbing wherever you see, something. I'm going to do 3 microns by 3 microns for the total feature. Since they are 5 features wide, that's going to come out to 600 nanometers center to center distance for those features. And I'm just looking at my notes here for something I've done in the past just to give us a good starting point. I did a 5 micron depth, which in this case is not calibrated, so it's not going to be 5 microns depth. I'm going to do a dwell time of 100 seconds. And when I come over here, you'll see that that means 97 passes. So I have 97 passes. In this case, I'm doing a scan direction of bottom to top each time. Some of the newer FIBs have the ability to, I think it's called like dynamic all directions. And it will go like bottom to top and then top to bottom and then left to right and then right to left. And that's pretty cool because that really helps with redeposition, kind of like evening out. Unfortunately, the older models, like the one we're on, do not have that. So I'm just going to do bottom to top, and it will go, however, left to right, right to left, left to right, right to left. So it like serpentines up. So at least that's better than always going, you know, in one direction. All right. So I think we're ready to go. The total mill time is 1 minute and 27 seconds. And I'll go ahead and get it started. You can see here that it is milling. There's not a whole lot to actually see while it's going until some stuff gets developed. But in approximately a minute, I'll switch over to the electron beam, and we should, if all goes well, see some well-defined features that are 600 nanometers center to center. All right. And after I do this, I'm gonna do a couple of times where I switch the size of the feature. I'm gonna make some features that are much smaller and show you what happens if I don't also lower my current. And then I'm gonna make some features that are much larger. So if you look closely, you can start to see some darkness form here. As I said, while it's scanning, it's also imaging. So this is the image it's creating. So I can see that I'm actually removing material and it is changing, you know, the image that's being produced. All right. Here we go. So now we've created in this minute, I'm gonna get this focus, not great focus here. Go. So you can see when we what we've done with this. So we've created these nice features, and you can see that you can indeed make some nice looking features pretty quickly, because that took a minute and 27 seconds. I'm not gonna. All right. So moving on. Oh. All right, moving on. Actually, let me show you. Like you can see the features that I just made in the focused ion beam. Now, I probably don't want to sit here. If I care about those features, I don't want to sit here. I am going to actually do it to show you why you don't see this. If I want to like refocus and like spend all this time looking at these features, remember, I'm milling away at my features while I'm doing this. So you see that my features look different now. And that's because I've kind of ruined them by doing all this extra imaging with them. So it is important, like if you've got features you like, don't look at them in the FIB. Generally not good. All right. But I don't need these features right now, so that's fine. All right, so now I'm gonna come back over here. And I'm going to, I guess I'll start by making smaller features. I'll probably do, let's see, I want to make them look bad. Okay, I'm gonna do 2 by 2, which should bring me down to, let me check my notes and make sure that I'm doing something bad. Oh yes, okay, this will do something bad. All right. So I'm gonna go ahead and get this started. I haven't changed the other conditions other than that I've shrunk the size of my bitmap so that it's now 2 by 2. So I should have 400 nanometers center to center distance. And the reason I'm telling you that I think this will make not the best feature is I've kind of shrunk this bitmap to be small enough that I've below the good resolution of the current I am currently at. So I'm currently set to 1 nanoamps, which is kind of middle of the range for currents. But 400 nanometer features need smaller resolution in order to create them. So this is a case where I've shrunk the bitmap enough that when I'm milling, say, the edge of one feature, I'm also milling the center of that same feature. And so I can't make well-defined features. So when we finish scanning this, I'll show you what we make, and it will probably look like basically a hole. Like I'll dig a hole, but I won't have made any features inside of that hole. Or if there are features, they're going to be very poorly defined, because if I wanted to make 400 nanometer features, it's very possible, but I need to turn down my current in order to do it. So as soon as this is done, I mean, I can already tell that bad things are happening here in the image that it's creating, because I don't see like these nice features. Instead, I see what kind of looks like a hole. So let's see, here is what I created. As you can see, it is a nice big hole. So you don't want to make, if you see something like this and you don't see like these nice well-defined features, it probably means you need to turn down your current, which in this microscope is here. As I said, I was at 1 nanoamp, and it's kind of in the middle. If I wanted to do 400 nanometer features, I would probably go to 0.5 or 0.3 nanoamps, and I'd try again. And I'd be willing to bet that it would take a little longer, because with lower currents, I have fewer ions coming at my sample per second. So my sputter rate is going to be lower, but I'm able to get those smaller, more well-defined features. All right, now I want to show you, and I'll show you what it looks like here too, actually. So you can kind of see there's like some semblance of features, but it's really just a giant hole, and they all kind of smear into each other. So I want to show you the other example of what happens if I make features that are just too big for my current. So I'm going to go ahead and, let's see, maybe I'll do 10 by 10. I got to zoom out a little bit here. So now, because my bitmap is 10 by 10, we'll go over here for my features. So now, because my bitmap is 10 by 10, each individual feature is spaced by 2 microns. So the center to center distance is now 2 microns. I'm just giving it a second to like clean out this space before I get started. All right, and I'm gonna go ahead and start this. So I have much bigger features. So I'm gonna have actually the opposite problem from what I had before when I tried to make tiny features and dig a hole. Now I'm going to make much larger features, but I kind of can't rely on this hole. My beam shape helps me FIB away places that I, want fibbed away, but don't necessarily have the machine fibbing at right now. And in particular, what I'm talking about is these corners. If you can remember, and you'll see it in a second when the pattern finishes. If you remember, I don't fib very much between the features. I kind of have those circles that define the outside of my feature, and then I only fib a tiny bit at the corners between the features. And when I'm making a smaller feature, that's fine, because when I'm fibbing the outside of my circles, I end up just fibbing away those corners anyways. But now that I've zoomed out, I've made a bigger feature without changing the resolution by changing the current. You'll see that actually you end up with maybe stuff you don't want. So let's see. All right, so here's my features. They're kind of short and stubby, which makes perfect sense because, I'll take an image that's a little clearer. They're kind of short and stubby, which makes perfect sense because I didn't actually scale up the amount of time I was fibbing, even though I expanded the area I was fibbing, so the time per area was less. But I didn't want to spend 20 minutes making features here. But what I do want to point out is the top of these features are completely flat because I no longer have that beam shape making the features nice and tapered, if that's what you want. And then I also have these little bumps between the features because, as I said, in between the features here, I'm not actually fibbing very long. When I scale my features down, those kind of get washed out by the beam, like the sides of the beam. But when I scale my features up, I no longer have that. Now, again, what I could do is I could increase my current, which makes my beam larger. And then I could probably make these features not only faster, but more like the shape I want. So there's just this interplay that you have to think about between your current and where you're milling and, the final feature shape and height that you want. So I guess that comes back to that earlier question. Is there a lot of trial and error? Yes, there is a lot of trial and error in this to really fine tune what you want. Yeah. So I think the last thing I wanted to show you guys was the stream files. So I'm going to move to a new position to get that started. So in order to make a stream file, I just click stream file here and I draw a little box. And then I upload a stream file and I've already created this one just as like a demo. You can see it here. It starts with S16, it's one pass, and there's 1,500, or I guess almost 1,600 lines. And then each one of those lines talks about how long you should spend at the point, and then the X position and the Y position. Because it's an X position and a Y position, you have to remember that when I zoom out and I zoom back in, my stream file does not change. So that can be a little bit dangerous because if you say wanted your total patterned area to be 5 microns on one side, and you set it all up to be 5 microns on one side, and then you change your magnification and don't realize it, then your pattern is no longer 5 microns on one side. Whereas if you're doing a bitmap and you zoom in and out, it's always compensating for that because you just, tell it, I want my pattern to be 5 microns on one side, and it does that always. All right. So this is just a very basic pattern. This is really just for demonstration purposes. All this does is do a spiral and then finish. But I did want to show you guys that. I think I'm going to zoom in a little because if my magnification is reasonable, it should make like a nice micro lens. So let's see. I'll try that. So I'm just going to run that real quick. For some of the longer stream files, you can actually see where it's going. This one, because it's a shorter one, it just kind of pops up every couple of seconds. But you can see that it started with the center bit of the spiral, and it's still going, but it's not showing me as it updates. All right, and so it's not the prettiest, but it's made like a little micro lens here. Let's see. Get this image. Yeah, as I said, not the prettiest, but it did make a little bit of a micro lens, and it did that by starting in the middle and spiraling outwards. So yeah, I think that's pretty much all I have to show you guys, but if there's any questions, I'm happy to answer them. So the question is, when using bitmaps, is there a way to get the exact Z values besides trial and error? Honestly, a lot of times I do use trial and error. And then I will kind of, let's say, do some math to compensate. I'll say, if you're talking about Z value, that's like the height of the feature. So if I say I'm aiming for like a 5 micron tall feature, and then I do my patterning and it comes out to be 4 microns tall, then I'll add 25% to my dwell time or to my total milling time in order to create a taller feature. Likewise, if you want to get, a nice feature shape, and say I got this feature and I wanted it to be a little bit skinnier, I have written a little bit of MATLAB code that can kind of like compensate a little bit for my feature shape, but oftentimes I often find it just easier to do a little bit of trial and error and say, oh, I want these features to be a little bit skinnier, and like make slight adjustments to my bitmaps to compensate. So yes, you can use math to compensate, but sometimes it's just easier to do a little bit of trial and error and tweak things until you get what you want. All right, so back to stream files. So the question was, how does one generate a stream file, and what are the advantages of using one? The advantages, I would say, are that you can have precise control over where your beam shape, where your beam goes. So especially if you want like really precise control over like redeposition and you wanted to like do little spirals. Here, let me go up to a couple of slides. So if you wanted to do what's on the right here, you would probably need a stream file in order to do that. Perhaps there's some fancy programs that can do this as well. Certainly there's nothing built in the FEI or Thermo Fisher microscopes that can do this. You would need a stream file in order to do the spiral scan on the right. How do you make them? I usually use either custom Python code that I've written to make these stream files, and I use equations to define where I want my beam to go. Or there are a couple of freely available stream file generators out there. I don't have a particular one that I recommend, but there are several. I unfortunately can't share my personal one because it's kind of like trade secret at our company, but I can say there's some really good ones out there that are available. I also see Greg asked, if anyone has tried to use ultrasonics or etching to remove redeposition. Seems like material would no longer be crystalline. It's true, the redeposited material usually is amorphous. I've never heard of someone trying to use ultrasonic or etching to remove it, but that could be something interesting because indeed it's usually known to be amorphous versus, the crystalline material it probably started as.